this video, we're going to review the difference between linear versus log scales and how to read these different types of scales. So just as a reminder, when we're talking about logarithmic or log scales for short, these are used when the values that you care about span several orders of magnitude. So in other words, when there's a tremendous range of variation in the parameter that you care about. Now, just to remind you what we mean when we talk about an order of magnitude, the range of 1 to 10 is 1 order of magnitude. (10 to 100 is another order of magnitude. 100 to 1,000 is another order of magnitude, and 1,000 to 10,000 is another order of magnitude. So basically multiplying by 10. Now, one example from fluid mechanics where this is needed or useful is the Reynolds number. So the Reynolds number spans about 25 orders of magnitude across the entire variety of flows that could be studied. And just as a reminder, Reynolds number here is rho v d over mu, where v is some characteristic velocity, d is a characteristic size, rho is the density, and mu is the viscosity. And just to illustrate this tremendous range in Reynolds number, I'll do sort of a number line or scale here to represent this. So down here at the bottom left, we'd have a Reynolds number of maybe 0.0001, which is 10 to the negative fourth. So this is our Reynolds number plot here. And this would correspond to things like bacteria swimming. So these very, very small organisms that are moving through the fluid would have a Reynolds number of about 10 to the negative fourth. Now moving up the scale a little bit, we could go to a Reynolds number of about 10, which is 10 to the 1, and this would correspond to something like tiny insect flight. So if we have a millimeter scale insect that's flying through the air, the Reynolds number of the flow around its wings would be about 10. Now moving up further by several orders of magnitude, we could go up to, say, 1,000,000. So a Reynolds number of about 10 to the sixth. This would correspond to an automobile, some sort of car, maybe on the interstate driving around. If we go even higher, we get into the realm of geophysical flows. So here I'll just write 10 raised to the 11th. This would be something like the Gulf Stream. So this geophysical flow that moves across the surface of the Earth, or other types of weather-related flows. And then up at the very top, we'd get something like 10 to the possibly more than 20th, where we get into things like astrophysical flows. Of course, most of our engineering applications are going to be in the range of several million down to less than 1 for microfluidics, for example. Now, that's an example. So when do we use linear scales and when do we use logarithmic scales? And what do they mean? So in linear scales, or on a linear scale, equal distances correspond to equal differences. Right, so if we have a number scale here, we go from 0 to 10 to 20 to 30 to 40, etc. So equal distances here correspond to equal differences. In contrast, on a log scale, equal distances correspond to multiplying by 10. All right, so if we again start with our scale here, we'll start with 1, multiply by 10, we go to 10, multiply by 10, go to 100, multiply by 10, go to 1,000, multiply by 10, go to 10,000, etc., etc. So correspondingly, we'd have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, etc. Now, sometimes we'll have a plot on which both of the scales are log scales. And so we call those log-log plots. And I'll draw one for example here. So for example, on the x-axis, we might have 1 right here, 10 right here, and extending this a bit, maybe 100 right here. On the y-scale, we might have 0.1 here, 1 here, and 10 right here. Now, sometimes there's also smaller ticks on the scales that give you further information about where you are. So for example, you might have scales here, 2, 3, 4, 5, 6, 7, 8, 9. So this tells you that when you pick sort of the middle line between 1 and 10, that's not going to be the midpoint between 1 and 10. That's not going to be 5.5. It's going to instead correspond to about 3.2. That's going to be your value right there. And so we have to remember that these scales are uneven in between the major ticks as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And so, for example, if we had we might extend this out here. So we have 20, 30, 40, 50, 60, 70, 80, 90, 100. And so if we have a plot that is maybe out here somewhere, or a point that's out here, we would have to read this by going, extending a line down here. This would be at, so we have 20, 30, this might be at around, say, 32, and then extending this line here, this might be at about 2. So our x and y point here would be about 32 and 2. And so that's how you would use a log-log plot.